Hello everyone. Today we are going to continue our discussion of word problems. We're looking at Unit 1, Lesson 6. We're going to solve word problems related to linear systems today. So similar to yesterday, we'll get them set up, but we'll actually work through using substitution or elimination to solve them. So your first example is one adult ticket for Medway School Play costs $6 and one student ticket costs $4. On opening night, 750 people attended the play and the total receipts were $3,890. How many adults were in the audience? So we have two different types of tickets. We have adult tickets and we have student tickets. So let's give a variable to each of those things. Let's let A represent the number of adult tickets sold, and we will let S represent the number of student tickets sold. Okay, so then we'll try to take each of these sentences and break them down into an equation. So we'll do equation 1 first here. It says on opening night, 750 people attended. So we have 750 people. So of all the adult tickets we sold and of all the student tickets we sold, the total of those two is 750. So let's represent that. So the number of adult tickets plus the number of student tickets is going to be 750. Now then it looks like it gives us some information about the money that was brought in, the revenue brought in by the sale of the tickets. So it says that an adult ticket is $6, a student ticket is $4, and the total dollar amount earned was $3,890. So we're going to put those values, multiply them by the number of tickets. So example, the number of adult tickets times $6, so 6A, plus the dollar amount for student tickets, so 4S, is going to equal that 3,890. All right, from there we should figure out which method we're going to use, substitution or elimination. And because we have the variables over the variables and the constants over the constants, let's use elimination. So we have to get the magnitude the same on one of these. I'm going to work to get the magnitude the same on my A variable. So I'm going to multiply this first equation by 6. So we're going to end up with 6A plus 6S. And then if we do 750 times 6, you should get 4,500. Okay, and I don't have to do anything to my equation 2 because I already have a 6 on my A. We have the same sign on our magnitude of A, so now we can eliminate that by subtracting. And we will just write, let's make sure we write, communicate what we're doing. So we have equation 1, we have equation 2. We're going to do 1 minus 2. So 6A minus 6A, those are going to cancel out. We have 6S minus 4S, so we'll have 2S. And then that 4,500 minus 3,890 is going to be 610. And then we'll just use algebra to solve for S, and we should get that the number of student tickets is 305. Okay, so then we'll go ahead and sub 305, or we'll sub the S equals 305 into the easier equation, which equation 1 looks a little easier. So equation 1 is A plus, and then instead of S, we're going to put our brackets there, and we're going to substitute in that 305. And then we'll subtract 305 from both sides, and we'll get that the adult tickets are 445. Okay, we could work through and do a check in equation 2. I'm going to leave that check for you guys to take a look at if you want. So let's just answer the question. So the question was, how many adult tickets were in the, or sorry, how many adults were in the audience? So we found that as our last variable. So we can say, therefore, there were 445 adults, or adult tickets were sold. Okay. Let's take a look at the next one. An investment club invested part of $20,000 at 14% per year and the rest at 12% per year. If the annual income from these investments is $2,660, how much was invested at each rate? So hopefully this looks similar to that chocolate question we did on the previous day lesson where we have some problems, some percentages. So this looks like it's a mixture problem. So we're going to have a table of values we're going to set up here. Okay, let's first identify what are those variables again. So it says an investment club invested $20,000. That investment had something that made 14, oops, thought I was on my highlighter. That was at 14% per year, and it had another part of the mix was 12% per year. So those are going to be our two investment variables. So we'll just let them be A and B. So let's let A represent the 14% investment. And let's let B represent the 12% investment. Okay, so we'll try to set up our table of values to hopefully understand how much we're going to have here. So we have our two investment types, just like we had those two types of trail mix yesterday or in the previous day's lesson. So we have investment type A and we have investment type B. And then we have some percentage return that each of these are going to yield, or that each of those are going to result in. So investment type A is going to return 14%. We'll write that as a decimal. Investment B is going to return 12%. Okay. And then in terms of how much money are we going to make on this return? Well, you're going to make the percentage of whatever it is you invested. So if I were to invest $10,000 of investment A, I'm going to get 14% back on that. Okay, if I was to invest $5,000 on investment B, I'm going to get 12% back on that. So how do we represent that with a mathematical expression? We would say that 0.14 times A, so times whatever we invest in A, is how much money we're going to get back. And the same is true for B, so 0.12 B. So now we have to figure out what do these kind of add up to based on what they told us. So this, it says that an investment club invested part of $20,000. So they're basically saying that if we were to take A and B, the total amount, let's just change our color, total amount here would be $20,000. Okay, so we have investment A and B. We're going to add those together to create a $20,000 investment. We also know that if we were to add the dollar amount or the return we get on each of these investments, then that return is going to be $2,660. Okay, so if we were to add the return from investment A and the return from investment B, it should be $2,660. Okay, so those really represent our equations. That return part in the middle is just to essentially help us identify that expression for what the return will be for investment A and investment B. So we're going to use each of these columns to set up our equations. Okay, So we're going to say that equation 1 is A plus B equals 20,000. And equation 2 is going to be that 0.14A plus 0.12B equals 2,660. Okay, so we can decide if we want to use substitution or elimination. Because we'd have to multiply by decimals to use elimination, I'm going to use substitution because I think it's easy to rearrange one of these equations for A and B. So I'm going to use substitution. All right, and I'm going to just communicate what I'm going to do here. So I'm going to rearrange equation 1 for A. So my equation 1 now, I'm going to move B over to the other side of the equation. Okay, and then I'm going to sub equation 1 into equation 2. So we have equation 2 is 0.14, and then instead of A, I'm going to put my brackets here because that's what I'm going to substitute in. So I'll have 20,000 minus B plus that 0.12B equals 2,660. And then we will just distribute that into our brackets. So we'll get 2,800 minus 0.14B plus 0.12B equals 2,660. So then we'll just move some stuff over to the other side of the equation and combine our like terms. So 0.14 negative plus 0.12, you're going to end up with a negative 0.02b. And when I move 2,800 over to the other side, you're going to get a negative 140. And then we'll just divide both sides by that negative 0.02. So B will equal 7,000. Okay, I'm running out of room a little bit here. We will try to squeeze in this last little bit, so we need to figure out what G equals. So we're going to sub B equals 7,000 into, we'll put it in the easier equation, so we'll put it into equation 1. So if we do A plus 7,000 equals 20,000, we'll bring our 7,000 over to the other side, and you should get that A equals 13,000. Okay? So again, I'll leave the check for you. We've kind of squished it in here at the bottom. So it says how much is invested at each rate. So I will just write my therefore statement over here. So therefore, we can say that $13,000 is invested in type A, so that's at 14%, and $7,000 is invested in type B, which is at 12%. That one is a little squished in there. Let's look at one more example. This next problem is also a mixture problem, but it involves our distance, speed, time triangle. So what I mean by that is when we are looking at distance, speed, or time, we use a triangle in math that looks something like this. It's distance, speed, time. So we put it in this triangle because it helps us remember the equation. Like we could say that the distance equals speed times time, because we have the s and the t next to each other to represent multiplication. If you wanted to rearrange this at all, so if we wanted to do what does speed equal, we could see that if I put s here, right, like s, this looks like now we have d over t next to speed. So we would say speed equals distance over time. And the same is true as if we looked at time. If we looked at time and then kind of paid attention to what do distance and speed look like next to it, well, again, it looks like distance over speed. So we put it in this triangle basically so we can look at how we would rearrange it for any of those given variables. So we could say that time is equal to distance over speed. So it's just a matter of how we can recognize how we rearrange that equation in any given sense. This next problem is going to involve this distance, speed, time equation. So I just wanted to show you that triangle before we got started. So it says a swimmer can swim 18 kilometers downstream in a nearby river in 3 hours. However, the return trip upstream takes him 6 hours. Find the swimmer's average speed in still water and the speed of the river's current. So it's asking us right there at the end, find the average speed in still water and the speed of the river's current. So let's write some variables to represent that. Let's let A represent the average speed. In still water. And we will let C represent the speed of the current. Okay, so some things to kind of think through logically here. We're going to set up our table. And we're just going to we have two paths that the swimmer is taking. They're going downstream first, and then the return trip upstream. Okay, so I want us to think a little bit about, we're going to set up our columns using this distance, speed, and time equation. So we're going to say the rate, or again, in this case, we're just talking about speed, times the time it takes is going to equal our distance. So if I just set up my table, we're just going to set it up with those three things, because remember, our rate, just like we saw in the triangle, our rate or our speed times time is going to equal our distance. Just like in this equation we saw up here, distance equals speed times time. So some things to think about here. We haven't really talked about currents or how we come up with an equation with there, but if we think logically, if we're swimming or if we're rowing a boat and we're going downstream, the current actually helps us. So we can add the speed of the current to whatever the speed is at which we're going, because those two speeds together create our total speed. Okay, so when we're going downstream, whatever our average speed is, plus the current is going to be the speed at which we're traveling. Okay, and then when we're going upstream, okay, that current's going to be working against us. So whatever our average speed is, our current's working in the opposite direction. So that's actually going to be subtracted from whatever our average speed is. So when we're going downstream, the current is a plus, and when we're going upstream, we're working against the current. We actually have to take that into account and take it off of the speed we're traveling at. All right, so it says that the swimmer can swim 18 kilometers downstream in 3 hours. So let's just highlight that. So 18 kilometers downstream in 3 hours. So in 3 hours, they're traveling 18 kilometers. From there, it says the return trip, however, takes him 6 hours. So when he's going upstream, it's going to take 6 hours to go that same 18 kilometers. Okay, so this table is essentially what we're going to use to set up our equations. So we know that rate times time equals distance. So we're going to have we'll put our rate here first. We're going to have our rate times time is going to equal our distance, which is 18 kilometers. And then our equation 2 is going to be the same thing. Our rate, which is a minus c, times 6 equals 18 kilometers. That's our equation 2. Okay, so let's first go ahead and distribute into our brackets to simplify these equations. So for equation 1, we're going to have 3a plus 3c equals 18. And for equation 2, we're going to have 6a minus 6c equals 18. Okay, we have all of our variables stacked over each other, so we're going to use elimination to solve this problem. For equation 1, I'm going to multiply by 2 to get the same magnitude on my variable. We don't have to do anything to equation 1, to equation 2. So equation 1 is going to become 6a plus 6c equals 36. And we'll leave equation 2 alone. Sorry, that should be a minus. Okay, we have that equation set up now. We have our equations right over each other. Go ahead and continue with elimination and see if you can solve for A and for C, and then write your therefore statement. Okay, and then come back to the video to see the solution. Okay, so if you continued on with elimination, hopefully you identified that C was going to be 1.5 and A was going to be 4.5. So let's just conclude with a therefore statement. So therefore, the average speed in still water is 4.5, and make sure we put on our units of measure there. This person is going in terms of kilometers per hour, and the speed of the current is 1.5 kilometers per hour. Okay, so lots of different types of questions today. Really, when we have these mixture type of problems, or even these distance, speed, time problems, setting up a table can be really beneficial to kind of see what the equation is going to look like. Okay, that is all for today.